Welcome students to our first video lecture for our semester. In this video segment we will cover two things. We'll cover an introduction to trigonometry, which is not part of our textbook, and section 2.1 from our textbook, angles and their measure. Just so you know ahead of time, this video segment is probably going to be quite long, so you might want to plan on at least two or more sittings for taking in this information. So the first thing I'd like to do is to give you an introduction to trigonometry. That is, what is trigonometry and where does it fit into your mathematics sequences as science majors. Most students who take trigonometry are in fact majoring in a STEM field: science, technology, engineering, or mathematics. And it's a very, very important topic. So let's take a look at what trigonometry actually is. So we'll address this question first. What is trigonometry? Trigonometry. Most of the time, we don't have to write out the word trigonometry. Most of the time, we'll just write trig or say trig to mean trigonometry. So we'll start with an example. Suppose I want to find out how tall a tree is. Not a real exciting example, but a kind of a classic example. Suppose I want to determine how tall a tree is without actually climbing the tree with a tape measure and figuring that out. So here's our tree. Have an ugly tree, and I want to measure the height of that tree without climbing that tree. So what I'll do is I'll put a little line segment up the tree. We kind of have to assume something big here. We have to assume that the tree is popping out of the ground at a right angle. And what I can do is use a tape measure to measure distance along the ground. And also I can use the shadow cast by the tree from the sun. So at a particular moment in time, suppose we have, here's our sun, happy sun, here's our sun, and suppose we're standing on the ground, say at this position right here, and we note two things at a particular moment in time. We note the position of the vertex of this little right triangle that I've drawn, or big right triangle, and we measure a couple parts of the right triangle. We measure the distance from us to the base of the tree. So this distance right here is something that is easy to measure. Just lay the tape measure down, mark off the point where the tip of the shadow is, and measure the distance from me or us to the base of the tree. Then, without waiting too long, I can also, without too much difficulty, I can measure the distance, or not the distance, but the angle of elevation up to the sun. Okay, of course I'm probably going to be wearing welding goggles so I don't fry my eyes out, but this is also fairly easy to measure. So this is easy to measure. Okay, at this point I'm looking at a triangle where I know three parts of the triangle. I know two angles, one of which is a right angle, 90 degrees, and I know a side. Well, it turns out that as long as I know three pieces of information about a triangle, and we're going to discover this in our course. It was probably discussed in a your geometry course prerequisite. But if you know three parts of a triangle and one of those parts is a side, the length of a side, then you can measure any other part theoretically. Okay, in particular, you can measure that vertical part of the triangle here, which we're calling, let's say, h, the height of the tree. So essentially, that's what trigonometry does. That's what trigonometry does. The word trigonometry has two parts. Trigon means a figure with three sides, and metry means measure. So trigonometry is really a part of geometry. Geometry, the word geometry means comes from geo, earth, and metry, measure. And so it comes the name comes from its early applications in measuring different aspects of our planet and stuff. And trigonometry is that part of geometry that uses triangles to measure things. Okay, so why is it so important to have an entire course based on this little part of geometry, kind of a big part of geometry, that uses triangles? Well, for exactly the reason that I mentioned. If we know any three parts of a triangle and one of those parts has to be a side, then we can find indirectly. We don't have to actually measure the other parts of the triangle. We can use some sort of formulas, and we're going to be looking at a lot of those formulas to indirectly measure the other parts of the triangle. So for our application, I don't have to crawl up the tree with a tape measure. I can actually measure the height of this tree indirectly. Okay, well, that's not a real exciting example. A little bit more interesting example, or a couple of them actually, come from astronomy. Not astrology, it's astronomy. Before we went to the moon as human beings, before we landed on the moon in 1969, we had to have a pretty good idea of how far the moon was away from us. It's kind of obvious that we need that information. Essentially, we need to know how much gas to put into the spaceship to get out there. So we kind of need to know how far I'm really oversimplifying it, but we kind of needed to know how far the moon was away before we attempted to set out for getting there ourselves. So how we did that was by using a sort of much grander example of the tree problem. So here's essentially how that goes. So here are a couple of circles that are meant to represent our planet Earth and the moon. So what we could do to estimate the distance to the moon is we could construct a triangle where we know three parts of the triangle, and one of those parts is going to include a side. So we have to start out with the idea that we're already familiar with the geometry of our planet. We know that it's approximately spherical, so we know we can measure distances on our planet indirectly. So, for example, or specifically, we could at some point in time, we could observe a specific angle to the moon. Okay, standing on the planet at, say, this point P, we can measure the angle that I have pictured here. Okay, we can obviously measure the angle of elevation up to the moon, and since we know the geometry of our planet, we could get the entire angle I have pictured there. We could wait a little while and do the similar thing. Not wait a little while, but we can imagine moving along the planet a particular distance to form an isosceles triangle where the angle measured at, say, the point Q is the same angle. Okay, so what we have now is an isosceles triangle. Then, since we know the sum of the angles in a triangle are 180 degrees, we can measure this angle up here, and that angle has a very special name. It's called the twin parallax. And it is easy to measure, primarily because we know the geometry of our own planet. And again, since we know the geometry of our own planet, this particular chord is also easy to compute. Okay. Again, we know the geometry of our planet. We know if we take a cross section that we're going to get a circle, and so we can figure out the length of this chord. So what we have now is actually more than we need. We have a triangle where we know all three angles, and we know one of those sides of the triangle. So from what I said earlier, we can figure out. We may compute this. We can use trigonometry to compute this. And that is the approximate distance to the moon. This is a very, very important example. It's a little oversimplified. I really haven't gone through the mechanics of how to find those base angles of the isosceles triangle, and I haven't gone through the mechanics of how to find that distance that from P to Q, that chord. But nevertheless, since we do know the geometry of the Earth, we can figure those things out. Equally as important is we can find the distance, or approximate, or at least we believe we can, because we haven't been able to visit other stars, but we can measure the distance from the Earth to neighboring stars, not including our own star, the sun. So the way we would do that is very, very similar. In fact, the idea is exactly the same. So here's a representation of our sun and our position Earth at some point in time. And suppose we're looking at figuring out the distance to some neighboring star. These distances in my drawing are not at all to scale. The distance from our sun to the next nearest star, called Proxima Centauri, is extremely far away. The distance from the sun to the Earth is about 93 million miles. The distance from the sun to our next nearest star is about 4.22 light years. To give you an idea of the scale there, it takes light about 8 minutes from the sun to reach us. It takes light from the sun to reach Proxima Centauri about 4.22 years. So the distances here are not to scale, but this kind of serves the purpose. So what we can do is we know the geometry, just like we know the geometry of our Earth. We know the geometry of our solar system. In particular, we know our geometry, the geometry of our trajectory, our own trajectory around the sun. So, like I said, the distance from the sun to the Earth is about 93 million miles. So we know that distance. And at some particular point in time, we can measure. Imagine it would be at night. We can measure this angle, this little angle here. And then we could wait 6 months. Where will we be? Where will the planet Earth be in 6 months? Well, that's not rocket science. No pun intended. In 6 months, we are going to be in a position, this doesn't look like a circular orbit, but in a position along the diameter of this gigantic circle, whose radius is 93 million. And we will have the corresponding same base angle of this huge isosceles triangle. So why are we doing this? Why don't we just do the same, use the geometry of the Earth and replace the position of the moon in my previous drawing with the distant star? Well, the problem is that the chord in my original drawing, PQ, is much too small to be of any effective use to compute the distance to the nearest star. The distances in the triangle that we use need to be huge. Okay, so 2 times 93 million miles will give us this base of this very, very large isosceles triangle. Again, since we know the geometry of our solar system, that is that easy thing to compute. We've also measured the angles pictured in this isosceles triangle. So since again the angles add up to 180 in a triangle, 180 degrees, we can measure the twin parallax to the star, and we now know three parts, actually know 4 parts of a triangle, but we know the minimum, we know 3 parts of a triangle, and one of the parts is a side, so we can figure out theoretically any other side. Namely, we can figure out the distance from the Earth to Proxima Centauri or other heavenly bodies in our universe. Okay, this is important. A lot of astronomy is based on using trigonometry to come up with computations this way. Okay, of course, distances to stars and other objects in our universe are verified by using other methods, but this is an old and tried and true method for computing huge distances indirectly, and that is trigonometry, measuring objects using triangles. Okay, so the next question I'd like to address, or the next kind of topic along the lines of giving you a nice introduction to trig, is why? Why in the sciences would we need such a thing? Well, my two examples here, 3 examples, including the tree example, kind of give you part of the answer there. We need trigonometry to have astronomy work out for us. I want to be much more general about this because a lot of people aren't going to be astronomy majors. So why trigonometry? Why? And the answer to the question, why is trigonometry so important in STEM mathematics? The answer to that question is that STEM majors need to take calculus. Calculus is the mathematics of motion and change. So what I'm going to do is I'm going to draw a little rectangle here, and in that rectangle I'm going to put the branch of mathematics called calculus here. Calculus is the mathematics of motion, or more generally, change. So if something moves or if something changes, it absolutely requires calculus to study it. So why is trigonometry so important in STEM mathematics? Because to communicate in calculus, we need 2 very important things. We need mastery in algebra. Algebra is the language of mathematics, We need mastery, not just a cursory knowledge of algebra. Otherwise, you could get into calculus after taking your first Algebra 1 course, It's not enough. Algebra 2 is not enough. Intermediate is not enough. It requires mastery of algebra. That's why we have pre-calculus coming up after this course for you guys. It also requires, the study of calculus also requires a mastery in geometry. But that part of geometry, specifically that part of geometry called trigonometry. Trigonometry is the branch of the part of geometry where we use triangles to measure things. Okay, and you notice that those 2 things, the algebra and the trigonometry, they overlap. And where they overlap, you get the most difficult part of a trig course. Algebra and trigonometry overlap when you start studying aspects of triangles using algebraic formulas and stuff, and that's the most difficult part of our course coming up in roundabout chapter 3, specifically sections 3.3 through 3.8 are the toughest part of our course. In any case, it's absolutely required to master both of these topics in order to have a fighting chance in this branch of mathematics called calculus. Okay, algebra is the language, and trigonometry is that branch from geometry that we need to be able to use that language of mathematics and algebra to master calculus. And from calculus, you go into the sciences. All sciences. Every science requires calculus, and there are no exceptions. What happens in the sciences? In the sciences, we look for change. We look for change in physical quantities, the physical quantities in our universe. So it's absolutely required that we study calculus. Well, before we dig into our really long section, section 2.1, I think I want to head off a question that I get a lot is, well, why do, if I'm not a science major, suppose I'm a finance major, why do I have to take calculus? Why do finance majors have to take calculus? Well, think about it for a second. Off to the side here, I'm going to put something called business calculus. Business calculus. Calculus. Business calculus is it's very often a single course that is required for finance majors. So why would finance majors need to study calculus? Well, if you think about what I gave you as the definition of calculus, calculus is the mathematics of motion and change. In business, what moves? Specifically, in finance, what moves or changes? Money. Money flows. If it moves or if it changes, it requires calculus to study, and there is no exception to that. None. Now notice that the pathway to business calculus doesn't include trig. That's true. Business calculus is generally a one-course, watered down version of the kind of calculus that science majors have to take. Science majors very often have to take 3 or 4 courses and semesters of calculus. Well, you take those 3 semesters of calculus and remove all the science applications, which essentially removes all the necessity for trigonometry, and you have something called business calculus. Okay. So that gives you this. Up to now, you have a nice idea of what trigonometry is and why it's so important. So what I'd like to do is to get started on the actual materials for the course. On the materials that I've just talked about in the first 20 minutes or so up to now, I'm not gonna quiz you on this material or test you on this material. This was just for your own knowledge. I think it's important for you to know why it is you're taking a particular course and what that course entails. Okay, so let's start talking about the materials for the course. Let's take a look at section 2.1. So, what is an angle? Okay. Well, the author says that an angle is 2 rays drawn with a common vertex, and that's just fine. That definition of an angle gets the job done. I don't like it. I'm not going to make you choose. In fact, I'm not going to test you on what the definition of an angle is. That's from geometry, but I want to start from really the very beginning. I think that a more important way of describing an angle is to say that it represents the amount of rotation required to rotate a single ray, about its endpoint. It's the amount of rotation required to rotate one ray about its endpoint. So there's a ray, and let's call the position of the ray before we rotate it, we'll call its the initial position. And in fact, in terms of the angle, we're going to call this the initial side of the angle. Okay, well, it's the amount of rotation required to rotate the single ray about its endpoint. So when we're done rotating it about its endpoint, it's going to have its new position this way, as an example, and we're going to call that new position the terminal side of the angle. Terminal side of the angle. And these are standard vocabulary terms for our course. And what is formed is the actual angle. I think it's important to use a type of definition that includes the concept of rotation, physically rotating something, because we're heading toward calculus. We're looking for ultimately the mathematics of motion and change, and we're changing the position of one ray from one position to another. Okay, angles can be positive, angles can be negative, and angles can be zero. Angles that are measured in the opposite way that the clock ticks time are called positive angles. Okay. Angles that are measured in the counterclockwise direction are called positive angles. Angles that are measured in the clockwise direction are called negative angles. You notice the little arcs I'm using to represent the angles indicate the direction of rotation. So angles measured in the clockwise direction are called negative angles. Okay. Next, let's talk about the types of symbols used to designate angles. Symbols, letters used to designate angles. So letters for angles. In math or in physics more generally, any symbol can be used to represent any quantity. But there are common symbols used for various quantities. Common symbols used for angles are certain of the lowercase Greek alphabet letters. Okay. The first one looks like this. This is called an alpha. And this is what our small a is based on, is this letter alpha. It's not the letter A. It sort of looks like a backwards fish or whatever. This is our letter alpha. Another letter that's very common is beta. Greek small letter beta. And as I understand it, this Greek letter beta morphed into our Latin B. Another common letter in the Greek alphabet is gamma. Now, gamma looks sort of like a Y. In fact, my gamma doesn't look very nice, but I guess it gets the job done. This is a Greek letter gamma. Let's see if I can draw it better. No, that works. These are gammas. Okay. There are two other very popular letters. In fact, the most popular letter for an angle is the Greek letter, small letter theta, lowercase letter theta. And finally, the Greek letter phi, or phi. Okay, but these are not the only letters used to represent angles. Like I said, any symbol can be used to represent any quantity in math or in physics, and you're going to find that it's true that sometimes a capital Z is used for an angle, and sometimes a small letter Q is used for angle. You can use any symbol to represent anything, but for our course and generally in calculus and physics, these letters are used to designate angles. Okay. Next, we need to do something that's very common in the sciences, in particular in physics. We need to introduce what's called a reference frame. A reference frame is a way of identifying a specific location in space. Specifically in the plane, we do that by introducing a set of axes. The x and y axes will serve nicely. So let's do that. If we take an angle and place it so that its initial side, let me do this in maybe red. We position the angle so that its initial side is along the positive x-axis, and its vertex is at the origin. Then we have an angle that is said to be in standard position. So this angle in red that I've marked off as theta is said to be in standard position. So theta is in standard position if it satisfies two things. The first thing is its initial side is along the positive x-axis. Initial side is along the positive x-axis. And the second thing is that its vertex is at the origin. Okay, now keep in mind that both of these things have to be met in order for an angle to be in standard position. So for example, if I drew the angle theta like this, this angle theta is not in standard position. Which two of the two aspects of an angle in standard position is not satisfied? It looks like the vertex is at the origin. However, the initial side is not along the positive x-axis. So the initial side is along the angle in quadrant, along the side of the angle in quadrant 1, and that violates the one of the two aspects of an angle in standard position. So here's another one. Suppose I have an angle, let's do this. Suppose our angle is this angle. Oops, that didn't turn out real nice. Let me do this better. Suppose we have an angle pictured here. So here's the initial side, here's the terminal side, and here's our angle, let's say alpha. Alpha is also not in standard position. Alpha is not, just like theta was, alpha is not in standard position. An angle is in standard position if its initial side is along the positive x-axis, and this initial side is along the positive x-axis for alpha, but its vertex is not at the origin. The vertex is at some positive x value along the x-axis. Okay, so think about this one. Is this angle in standard position? So here's the actual angle in question. Here's the angle in question. And let's say this is the angle beta. So is beta in standard position? Well, check to make sure that the two aspects of an angle in standard position are met, or determine whether one or both of them are not met. Is the initial side along the positive x-axis? Yes. Yes, it looks like it started the angle at the positive x-axis. Is the vertex at the origin? Yeah, the vertex is at the origin. So this angle beta is in standard position. Beta is in standard position. Can you think about how else to describe beta? Beta is in standard position. What else can you say about the angle, just based on what I've said in this video segment so far? What else can you tell me about beta? Well, we haven't talked too much about angles yet. So what kind of an angle is beta? Beta is not measured counterclockwise, it's measured clockwise. So beta is a negative angle. Beta is a negative angle. Okay. So more about angles. There's a lot to talk about angles. That you wouldn't think that there would be that much to talk about. We're just scratching the surface. So what else about angles? Angles can also be characterized, angles that are in standard position, can also be characterized by the location of their terminal side. Okay, so let me repeat that. Angles in standard position can be characterized by the position of their terminal side. An angle drawn in standard position can be characterized by the location of its terminal side. So what do I mean by that? Well, I'm going to draw some angles and we'll talk about it. So I've drawn four angles. And each of the angles is in standard position. I would like to describe these angles another way. Well, I can describe them as positive or negative. Looks like alpha is a negative angle. It's measured clockwise. Beta looks like a positive angle counterclockwise. Theta is also a positive angle. And phi looks like a negative angle. It's measured clockwise. But alpha is called a quadrant 1 angle. Quadrant 1 angle, or quadrant Roman numeral 1, Q for quadrant Roman numeral 1 angle. Okay. Now remember from algebra, the quadrants are so we remember that the quadrants are quadrant 1, quadrants 1, 2, 3, and 4. This is how we label the quadrants. So alpha, the terminal side of alpha lies in quadrant 1, so we call alpha quadrant 1 angle. So you can kind of guess how we're going to name the others. Beta is called a quadrant 2 angle, or Q Roman numeral 2 angle. Theta is called a quadrant 3, supposed to be quotes here, angle, or Q Roman numeral 3 angle. Finally, phi is a quadrant 4 angle, or we designate it as Q Roman numeral 4. Okay, so if the terminal side of an angle ends in a particular quadrant, we name the angle according to that quadrant. So here's a really common true or false question. Here's a true or false question. Let me state it this way. By the way, if I write EX, that means example. So for example, true or false, true or false. If theta is in standard position, so if theta is an angle in standard position, then theta must be either a quadrant 1, quadrant 2, quadrant 3, or quadrant 4 angle. True or false? If you have some angle, any angle in standard position, it's got to be a quadrant 1, 2, 3, or 4 angle. Very often when I mention this true or false question in class, I hear a resounding wrong answer, and the answer is false. The answer is false. Absolutely false. Absolutely false. If you didn't see it, or don't see why, here's the angle. I'm going to draw an angle. Here's an angle. We'll call it beta. Beta. Beta, the terminal side of beta does not lie in quadrant 1, 2, 3, or 4. The terminal side lies on an axis. Beta is called a quadrantal angle. Quadrantal angle. So if the terminal side of an angle and in standard position ends on an axis, it's called a quadrantal angle. It's called a quadrantal angle. Okay? Okay. So, how many different ways can you describe the angle that I'm picturing now? How many ways can you describe the angle theta? Theta is what? Is it positive or negative? Well, of course, it's positive or negative. The only angles that aren't positive or negative is the angle 0. Well, theta is what? Theta is a positive angle. Theta is positive. Okay, what else? Is theta a quadrant 1, 2, 3, or 4 angle? No, it is a quadrantal angle. What else? Think about geometry. This particular angle theta is quadrantal, just like the angle beta was before, but this particular angle theta has one more way you use to describe in geometry. Theta is a right angle. Right angle. Without mentioning 90 degrees or whatever, theta is a right angle. Okay? Anything else? It's positive, quadrantal, right angle. Well, theta is in what? Standard position. Okay, so far, what we're looking at is a lot of vocabulary. The vocabulary doesn't make up the vast majority of the material for the course, but it's essential that we're all on the same page with words and stuff. So these terms are really important. Okay, so let's take a look at a few ways of measuring angles. A few ways that we have of measuring angles. We're going to look at first, and this is an unfortunate statement I have to make. Let's look at first the least popular way in calculus, which is where most people who take trig are headed, the least popular way to measure angles. And it's unfortunately in the way that we're most familiar with measuring angles, and that's in degrees. Okay, so what we're heading toward is talking about measuring angles. Measuring angles. How do we measure angles? Well, degrees. There are 3 popular ways of measuring angles. The last one is the most popular, and it's simultaneously the less intuitive way of measuring angles. So measuring angles, degrees. So let's talk about degrees. Degrees. So we'll talk about degrees not by stating what one of them is, although we'll ultimately lead there, but we'll describe what 360 of them give. 360 degrees gives us 1 revolution. We knew this before we took our first geometry class. I guess our only geometry class. Before we took geometry, we knew that 360 degrees gives 1 revolution. We grew up with this, so this is what makes degrees easy for us, is that we were trained, we grew up with degrees. Well, if 360 degrees is 1 revolution, then 1 degree is 1/360th of a revolution. Okay, we're going to spend very little time talking about degrees because we're all very familiar with them, but I'd like to do one example. So let's do one. Let's draw in standard position. Let's draw some angles in standard position, measured in degrees. So part A for the example, theta equals 45 degrees. Well, we know that a 90-degree angle is quadrantal, so a 45-degree angle should be a quadrant 1 angle that bisects the first quadrant. So theta equals 45 degrees, pictured thus. No big surprise. So let's take a look at another one. B. Let's say theta equals negative 30 degrees. Well, let's take a look at theta equals negative 30 degrees. So let's see here. Theta is a negative angle, and 30 is 1/3 of 90. So negative 90 would be quadrantal, would hit the negative y-axis. So 30 degrees is 1/3 of that. So 30 degrees, negative 30 degrees rather, would look about like this. If I tacked on another 30 degrees, I would have 60 degrees. If I tacked on another 30 degrees, I would have 90 degrees, negative 90 degrees. So we can see that about 1/3 of negative 90 degrees is pictured in my drawing. Okay, so how about one more before we move on to our next way of measuring angles? Let's take a look at theta equals 390 degrees. 390 degrees. Well, 390 degrees goes beyond a revolution. Goes beyond one revolution. So remember, one revolution gets us all the way around in the positive direction, 360 degrees. So 390 is 360 degrees plus an additional 30 degrees. So we travel around one complete revolution and then push into quadrant 1, 1/3 of the way into quadrant 1, another 30 degrees, and we're looking at 390 degrees. Okay. All right. So for the next, oh gosh, 10, 15 minutes or so, we're going to talk about a way of measuring angles that is not very popular in this course or in calculus. So why would we do that? Well, there turns out to be a way of measuring angles that is still very popular in a huge chunk of physics called astronomy. This way of measuring angles is called degrees, minutes, and seconds. So I'm going to spend about 15 minutes talking about this degrees, minutes, second notation or way of measuring angles. But I want to let you know it doesn't play a huge role in our course. Okay? So, what do we mean by degrees, minutes, and seconds? So, minutes and seconds give us a way of subdividing an angle into fractions of an angle. So what am I talking about here? So let's assume that we have an angle of 1 degree, and I'm going to blow up that angle. This is not going to be an accurate representation of 1 degree. This is more like 30 degrees the way I've drawn this. But suppose just for our discussion here that this angle measures 1 degree. And suppose I take that angle of 1 degree and I chop it up. 1, 2, 3, 4, etc., 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 etc. I cut it up into 60 equal subdivisions. Okay, so one of those 60 subdivisions, I don't know if I'm going to be able to draw this very well. I got lucky. Is in red. So this is one of the 60 equal subdivisions. Okay, so that one of the 60 equal subdivisions is 1/60th of a degree. Okay, and that 1/60th of a degree is called 1 minute. And it's an unfortunate use of the term minute because it has nothing to do with time. 1 minute is 1/60th of a degree, and it has nothing to do with time. It's just how we designate this subdivision of a degree, and we abbreviate it as 1 apostrophe. 1 apostrophe. Okay. So if 1/60th of a degree equals 1 minute, then 60 minutes is 1 degree. All 60 of those subdivisions equals 1 degree. Okay. So let's divide up the degree, the angle of 1 degree even further. Suppose we take one of those subdivisions that we call 1 minute and we blow it up real big so we can see it real big. So this angle here, which looks like 45 degrees, is really supposed to represent 1 minute. Okay, so what we're doing is we're taking, here's in green, we're taking that 1 minute from before and we're blow it up. Okay, now suppose we take that 1 minute and divide it up into 60 equal subdivisions. So we take that 1 minute and we divide it up into another 60 equal subdivisions. So each of those 60 equal subdivisions looks like about this angle in red. Now that little angle in red is tiny. That little angle in red right there is 1/60th of the 1 minute that I have, which itself is a tiny little angle. This subdivision is 1/60th of a minute, and this is called 1 second. Again, has nothing to do with time. And the abbreviation for second is the double apostrophe, is quotation, or whatever. That's, I guess it's what you use for punctuation, be a quotation mark. Okay. So there are 60 seconds in 1 minute. Okay. So how many seconds then, you're going to fill in the blanks kind of here. How many seconds is in 1 degree? Well, there are 60 seconds in 1 minute, and there are 60 minutes in 1 degree. So each of the little angles that I've circled in green, that's 1 minute. And inside of each of those little angles I've circled in green, there are 60 seconds. So there have to be a total of 60 times 60, or not 360, but 3,600 seconds in 1 degree. Now a degree is a tiny angle, small angle. And that small angle of 1 degree has 3,600 seconds in it. Okay, so what I'm doing is I'm sort of creating a way of subdividing the degree into tinier units. And those units are not decimals, they're minutes and seconds. So before we go into the degree, minute, seconds notation, let me give you kind of a feel for what a degree and what a minute and what a second looks like. So if you take a penny and hold it at arm's length, if you take a penny, 1 penny, and hold it at arm's length, so here's the penny, 1 cent, and you hold it at arm's length, which is like, let's say it's 3.5 feet. As soon as I said that, I thought, God, that's a long arm, but that's not that long, I guess. The angle that's formed, the angle that's subtended there, that's about 1 degree. You can imagine, you take your arm, hold it out at arm's length, and maybe squeeze your fingers, your index finger and your thumb to be holding that penny, imagining that penny. That angle that's formed there is 1 degree to your eye, from your eye. Now, if you take that same penny and you take it 215 feet. The penny somehow got big. You take that same penny and take it to about 215 feet. It's a long way. It's a lot more than arm's length. That angle formed now, you have to imagine that angle is going to be extremely tiny, but that's 1 minute. That's not 1 second, that's 1 minute. 1 minute is tiny. So if you take that same penny, this is not to scale. I don't even know why I'm drawing it. So drawing the little drawing here. You can draw them all the same size, just change the distance scale. So if you take that same penny and you take it 2.4 miles. 2.4 miles. I think that's about the distance from Cerritos College to like Del Amo. Not the fashion center, but the street. That one angle, it's going to be microscopic. That's 1 second. So why would we need such tiny angles? We would need such tiny angles in astronomy because the angles subtended from our eyes to stars out in space, they are extremely tiny. Okay, so that takes us to degrees, minutes, seconds notation. DMS notation. Degrees, minutes, seconds notation. Example of degrees, minutes, seconds notation is something like 32 degrees, 12 minutes, 15 seconds. There's no decimal place here. There's no decimal place here. This is a way of designating an angle that is 32 degrees, 12 minutes, and then 15 additional seconds. Okay, and this is called DMS notation. And again, it's very popular in astronomy. So for us, mostly we need to be able to convert from degrees, minutes, seconds to decimal degrees, and our familiar way of measuring angles in decimal degrees, and vice versa. Fortunately, the calculator does that very simply. So what I'm going to do is I'm going to describe to you how to use the Texas Instruments TI-84 calculator to convert from degrees, minutes, seconds to decimal degrees and vice versa. And then we'll move on to our last way of measuring angles. Okay. So if you want to play along and learn how to use your calculator, or to practice using your calculator to convert from DMS notation to decimal degrees and vice versa, maybe pause the video and grab your graphing calculator. Otherwise, you can just observe or take notes. So suppose I want, for example, to convert 32 degrees, 12 minutes, 15 seconds to decimal degrees. And this is a purely calculator problem. What you would do, and again I'm going to address the TI-84 Silver Plus, I guess it's TI-84 Plus Silver Edition. I think the TI-84s are all compatible. You would push 32 and then push second APPS, second apps, APPS. This is the angle feature in your calculator, which will make sense if you look at your calculator. So you push 32, second APPS, and you notice that if you do that, you have a sub-menu popping up with the first item, number 1, is degrees. So you push second apps 1, and this is for degrees. Okay, then you push, I'm going to do it at the same time, so make sure that it's actually working out. Then you push the 12, second APPS for accessing the angles feature. And that gives you, when you do that, you see the menu number 2 is, or the submenu, the number 2 is minutes. So you push 2. Okay, this gives you minutes. And then you push 15, or press 15, enter 15. And we don't press second apps at this point. If you were to do that, you're not going to see what you would expect to see. You see number 3, a small r, which means radians, and that's coming up. And the small r is not seconds. They've hidden the seconds from us. So if you went ahead and pushed second APPS again, push second mode for second quit. So you enter 32, second APPS 1, 12, second APPS 2, and then 15, then you push the green alpha button. I'll even write it in green. You push the green alpha button. That accesses the features on the buttons that are printed in green. You notice above the plus sign is a little double, or a quotation mark, or seconds. So you push 15, green alpha, and seconds, or green alpha plus, and that gives you seconds. And then you push enter. When you push enter, you should see the conversion to 32.2041, 3 6s, 7, so approximately that many degrees. Okay. Now, suppose we want to go the other way. Suppose we want, for example, to convert from decimal degrees to DMS notation. So convert to DMS notation. And the angle is going to be, let's say, 16.47 degrees. That'll work. This is easy. There's only one thing to do here. We would push 16.47 second APPS. Again, that accesses the angle features in your calculator. And number 4. And then enter. Enter. Okay. And you should see, let's see, 16 degrees, 28 minutes, 12 seconds. Okay. The final thing I wanted to mention before we move on to the most important part of actually the whole section is this last way of measuring angles. The last thing I wanted to talk about with the DMS notation is rounding off. If our angle, let's say we were dealing with an angle of, let's say 10 degrees, 15 minutes, 24.5 seconds. In our course, we want our angles to have all whole numbers of degrees, minutes, and seconds. Degrees and minutes are always whole numbers. They're never fractions of degrees or minutes. But the seconds can turn out to be fractions of a second. What we're going to do is we're going to round to the nearest second. So we would round to 10 degrees, 15 minutes, and how many seconds? It's either going to be 24 or 25. What do you think? 25. We use the standard method for rounding. And we would round then to 10 degrees, 15 minutes, 25 seconds. This is going to be our standard for our course. In astronomy, there's no such standard unless your instructor makes it a standard. You can have fractions of a second. but we're going to round to whole number degrees, minutes, and seconds. Okay. Okay. So let's finish our lecture with the video lecture with the most important part of the video lecture. Let's talk about angles measured in what are called radians. Let's talk about angles measured in radians. Now the discussion of radians is going to get quite complicated. So if you're a little weary right now, you might want to take a little break. Otherwise, let's dig into radians. First of all, it's unfortunate that we need them because they're not very intuitive to the user. It takes quite a bit of getting used to become proficient with radians. Unfortunately, they are the only way that we can measure angles in formulas in calculus and many of the formulas in physics. So we need to avoid using degrees in almost all of the formulas in calculus and physics. Okay, I'll explain why in a little bit. But right now, let's see what this mysterious radian is. What is a radian? How do we measure radians? So suppose we start with a circle. Suppose we start with a circle of, let's say, radius r. So here's a circle, and the radius is r. Now imagine taking a little line segment of length r. So here's a little line segment of length r. And imagine that little line segment is made of flexible material like rubber. And I'm not going to stretch it, but I want to bend it, and I'm going to lay it on top the circle. So I'm going to take this little radius line segment, and I'm going to lay it on top of the circle and bend it along the circle. So if I do that, I'm looking at this little portion of the circle. So that distance, that arc length, that's r. Okay, remember I'm not stretching out the line segment. I'm just laying it on top of the circle. Okay. Now the angle that's formed from the center of the circle, that angle right there, that's 1 radian. 1 radian. And that 1 radian doesn't depend on the actual radius of the circle. It doesn't depend on what the actual value of the radius is. If its radius is 5 or 10 or 15 or 1,000, or it doesn't make any difference. The same angle of 1 radian is always formed. So that's kind of weird. It's not intuitive for most of us. So what does 1 radian equal approximately in degrees? So 1 radian is approximately, we'll use a little squiggly equal sign for approximately, equal to 57.3 degrees. And that's just a rough approximation. 1 radian is actually an irrational decimal degree, so it goes on and on and on forever without repeating, just like pi is an irrational number. So that is bizarre. That's the connection between degrees, our familiar way of measuring angles, in this radian. Okay, so we need to do much better. We need to get a really powerfully good feel for radians in kind of a short amount of lecture space here. So let's think about answering this question. How many radians? So you see, 1 radian is about 57.3. How many radians does it take to get 1 complete revolution? Well, let's think about that. How many radians? That's an important question. How many radians? Not approximately, I mean exactly how many. How many radians are in 1 complete revolution? So let's think about that. So let's construct the answer to the question. I want to draw I want to draw an angle of one complete revolution using radians. So here's the first radian. The first radian would be 1 radian. So there's 1 radian. And obviously that doesn't get us all the way around the circle. So let's put another, or add to it, another radian. Here would be about 1 more radian. This arc length that I'm drawing now is another arc length of 1 radius. If I drew a third radian in there, it would not quite get us to 180 degrees, to a half a revolution. So here's another radian. That's unfortunate. It doesn't quite get us to half a revolution. So here's another one. Tack on another one. Another one would get us about right there. Probably should have drawn it a little longer, but that's okay. Here's another radian. I'm just laying bent line segments along the curve. Each of these little angles I'm tacking on is 1 radian. Here's the next one. And that's unfortunate. This is a whole number of radians. How many are there? 1, 2, 3, 4, 5, 6. So 1 revolution is equal to 6 radians, 6 times r plus a little bit. And that's really unfortunate. Okay, or 6 radians plus a little bit. That's just not cool. That destroys the radian as an intuitive counterpart to our angles measured in degrees. So back to my original question. Exactly how many radians do I get to get 1 revolution? Well, think about the concept of 1 revolution is 6 times r, 6r plus a little bit. But 1 revolution along a circle is not 6 times r. 1 revolution is not 6 times r. 1 revolution of a circle, the distance around a circle is the perimeter of a circle is called the what of a circle? The circumference of a circle is not 6 times r. What's the circumference of a circle? Very often students remember it's either pi r squared or 2 pi r. Well, it's 2 pi r. The circumference of a circle is 2 pi times r. It's not 6r. 6 radians around the circle would if 6 radians were required to get around a circle, the circumference would be 6r. The circumference is 2 pi times r. Okay. Where pi is the number that we're familiar with. Pi is approximately 3.14. Pi is an irrational number. It goes on forever as a decimal without repeating. It's approximately 3.14. So 2 pi r, 2 pi is approximately 6.28. So 1 radian, I'm sorry, 2 pi radians equal 1 revolution. 2 pi radians to get us all the way around the circle. And an unfortunate result of the use of the Greek letter pi is that we tend to think about pi as a dessert item that looks like a circle, whereas it takes 2 pi radians to get 1 revolution. So pi radians doesn't give you a full circle or full revolution. It only gives you half a revolution. So we kind of divorce our word pi, P-I-E, from the Greek letter P-I. Okay, 2 pi radians give us 1 revolution. 2 pi radians equals 1 revolution. Well, 2 pi is about 6.28. So look up above at my estimation of 1 revolution in terms of radians. It was 6 radians plus a little bit. So it was 6 radians plus, how much is the little bit approximately? 6 radians plus about 0.28 radians. Okay, off the decimal approximation for 2 pi. The important thing here is that 2 pi radians gives us 1 revolution. If you're not familiar with that, or if you don't remember that from geometry, you're going to want to memorize that. That's a hugely important thing for our semester. Okay. Well, if 2 pi radians equals 1 revolution, that means 2 pi radians equals 360 degrees. So 2 pi, there's a connection between our familiar intuitive degrees and radians. So if 2 pi radians equals 360 degrees, and divide both sides by 2, pi radians equals 180 degrees. So pi radians gets us 1/2 a revolution, or 180 degrees. This is the ultimate relationship between radians and degrees, that pi radians equals 180 degrees. Pi radians gets us all halfway around the circle, halfway around. Okay. Now, very briefly, I want to look at the answering the question, why do we need to use radians? Why can't we just use degrees in calculus and physics? Why do we need to use radians? And the answer is that radians are what's called unitless. Radians do not have what are called units. So what are units? Well, units are very easy to describe. If you had chemistry, you know exactly what a unit is. If you haven't had chemistry, here's the number 5. 5 is a unitless number, has no units whatsoever. But as soon as I do this, I've created units. These are units of dollars. As soon as I do this, 5 bananas, bananas are the units. If I do this, 5 degrees, degrees are the units. And the problem with degrees, angles measured in degrees, is they contribute the units of degrees to answers in calculus. So if you're putting 5 degrees into a particular formula in calculus or physics, those units of degrees are going to be translated into the units of the answer. So for example, we don't have something like speed measured in miles per hour degrees, and that's exactly what would happen if we used an angle measured in degrees in a formula that measures speed in calculus. We would have that additional units of degrees in the answer. So radians have no units. Well, if you're thinking, well, then why do you write radians? Why do you write the word radians? As soon as you write the word radians, it looks like you're putting on units. Well, it's just for convenience that I'm putting the word radians there. All I need to write is to describe the relationship between radians and degrees is that pi equals 180 degrees. I don't need to write radians. I only write the word radians, or abbreviated RAD, if I want to emphasize to the reader that I'm talking about an angle. Radians are pure, angles measured in radians are pure numbers. They are dimensionless numbers. Okay, so angles measured in radians have no units, so how could I better describe that? Well, in geometry, you learned a formula S equals R theta. It's a very, very important formula from geometry, If you don't remember it, this is your review of that formula. I think I can draw a better circle. This is a review of the formula. We'll need this formula for our course, but this is this formula S equals R theta gives us the relationship between the radius of a circle, the central angle in a circle, theta, and the arc length S along a circle. Okay. The arc length S around the circle is related to the radius by the S equals R times theta, where theta is the central angle. We'll solve for theta. If you divide both sides by R, you get theta equals S over R. Now, think a little bit more carefully about that last formula. S is measured in units of length, let's say feet. R is measured in the same units as S. R, the radius of a circle, is in, say, feet, or inches, or centimeters, or millimeters, or whatever. But units, the units of feet, are going to cancel out, as they do in what's called dimensional analysis. They cancel just like you reduce fractions. You cancel out numbers, cancel out units, and you have no units. No units remain. Theta is measured, an angle theta measured as a central angle is unitless in radians. Okay? Okay. To end this video segment, I would like to look at some common angles measured in radians. Now what I'm going to do is I'm going to tear apart a handout that I'm going to post on Canvas so that you can practice with this. So what I would like to do is to get used to some common angles measured in radians for our course. So from the handout, I've copied a circle, looks like a bullseye. What I'd like to do is to practice dividing the angle pi radians. So let's assume that we have 0 radians in standard position, an angle of 0. Then here's the angle pi in standard position. So pi, remember, pi is 180 degrees, half a revolution. If I take pi and divide by 2, then I get the angle pictured. So pi over 2 is 1/4 of a revolution. Pi is half of a revolution. The next angle I'd like to be able to identify. Well, that's easy to do. If you think about pi over 2 is 1/4 of a revolution. Pi, which is 2 pi over 2, is half a revolution. Then 3 pi over 2 I get by adding another pi over 2 to that. And then 4 pi over 2 reduces to 2 pi. And that gives me 1 complete revolution. So pi over 2 is 1/4 of a revolution. Pi is half a revolution. 3 pi over 2, or 3 times 1 pi over 2, 3 pi over 2 is 3/4 of a revolution, and 4 pi over 2, which reduces to 2 pi, is 1 complete revolution. Okay. So let's do this again with another subdivision of pi. Let's imagine taking the angle pi, that's half a revolution, and dividing it into 4 equal subdivisions. Let's imagine taking the angle 0, placing it in a standard position there, pi, half a revolution, and we're going to divide pi into 4 equal subdivisions. So the first subdivision would be represented by pi over 4. So this is 1 pi over 4. 1 pi divided by 4. 2 pi divided by 4 then would be another 1 pi over 4 added to that. But 2 pi over 4 reduces to pi over 2, which we mentioned is an earlier angle. If I add another pi over 4 to 2 pi over 4, I get 3 pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4 reduces to pi. I'm not going to actually draw them in. I'll just put the angles at the end of the dotted lines. 5 pi over 4 would be a quadrant 3 angle. 6 pi over 4, add another pi over 4 to 5 pi over 4, I get 6 pi over 4 reduces to 3 pi over 2. 7 pi over 4 is in quadrant 4. 8 pi over 4 reduces to 2 pi. And remember, 2 pi gives us a complete revolution. So 1 pi over 4 looks, in quadrant 1 pi over 4 looks like the 45-degree angle. 2 pi over 4, pi over 2 is 90 degrees. 3 pi over 4 is 3 times 1 pi over 4, or 3 times 45 degrees. 3 times 45 would be 135 degrees. 3 pi over 4 equals 135 degrees. Pi is 180, and so forth. Okay, so let's practice with another common subdivision. Let's imagine taking the angle pi, now, just as before, and divide it into 3 subdivisions. So if this is the angle pi representing half a revolution, I want to divide the angle pi by 3, then 1 pi over 3 will appear in quadrant 1. Notice that I don't have the y-axis pictured here. 1 pi over 3, that's 1/3 of pi. If I add another 1/3 to that, I get 2 pi over 3. So 2 pi over 3 would be a quadrant 2 angle. 3 pi over 3 reduces to pi. Kind of put these drawing a little close to my previous one. Let me see if I can move it over without destroying things. Let's do a little bit there. I don't know if it's gonna, there it is. Okay. So 1 pi over 3 plus another 1 pi over 3 is 2 pi over 3. And 3 pi over 3 is pi. 4 pi over 3, if I add another 1 pi over 3. Plus another 1 pi over 3 is 5 pi over 3. I'm adding this same angle 1 pi over 3 to the previous angles. 5 pi over 3 plus 1 pi over 3 is 6 pi over 3. Which reduces to 2 pi. So we recognize angles 1 pi over 3, 2 pi over 3, 3 pi over 3, etc. So 1/3 of pi, pi over 3, 1/3 of pi, pi equals 180. So if pi equals 180, pi divided by 3 should equal 180 divided by 3. So for specifically, pi over 3 is 60 degrees. 2 pi over 3 is 60 degrees times 2 would be 120. 3 pi over 3 would be pi, etc., etc., etc. Okay. So let's do this one more time. Let's take the angle pi and divide it not into thirds, but into 6 equal subdivisions. Okay, let's do that. So now let's divide into 6 equal subdivisions. So here's 0 radians. Notice that there's no, when I write 0 for an angle, I didn't write a little degree symbol. If this is kind of important, if you want an angle to represent an angle measured in degrees, you must use the degree symbol. If the angle doesn't have a degree symbol, it's a radian. Okay, I'm going to emphasize that as in my closing remarks. But let's continue here. We have an angle of 0 radians. And I want to draw now an angle of pi radians. And I want to divide the pi into 6 equal subdivisions. I've drawn all 6, in fact I've drawn 12 of them, but here I've drawn 6 subdivisions that we can visualize. The first one in quadrant 1 would be represented by pi over 6. And pi over 6, if I add another pi over 6 to that, I get 2 pi over 6. which reduces to pi over 3, which was in the upper right-hand corner of your screen. That's our 60 degrees. Plus another pi over 6 would be 3 pi over 6, which reduces to pi over 2, 90 degrees. 4 pi over 6, which reduces to 2 pi over 3. So these angles in radians, at least they satisfy something nice in terms of behaving like fractions, okay? So 4 pi over 6 plus another pi over 6 would be 5 pi over 6. 5 pi over 6 plus another pi over 6 would be 6 pi over 6, which reduces to pi as we should have. 6 pi over 6 plus 1 pi over 6 would be 7 pi over 6. Plus 1 pi over 6 would be 8 pi over 6, which reduces to 4 pi over 3. These are all very common angles in trig. 8 pi over 6 plus 1 pi over 6 is 9 pi over 6. Each of the angles I'm adding to each of the angles 1 pi over 6. Oops. 9 pi over 6 reduces to 3 pi over 2. Plus another 1 pi over 6 is 10 pi over 6. Reduces to 5 pi over 3. 11 pi over 6, which doesn't reduce. 12 pi over 6, one complete revolution, is equal to what it should equal, 2 pi. Now what I think you ought to do with this is do this over again using the handout that I'm posting on Canvas, and also saying it out loud to remind myself to actually post it on Canvas. Practice with these subdivisions until they're automatic for you. We're going to need to be able to recognize these angles in standard position through the whole course. So I thought I'd look at one example to maybe pull a lot of this stuff together. What I'd like to do is I'd like to look at an example where we assume that the angles that I'm drawing are in standard position, and I simply want to name the quadrant where the terminal side of the angle ends up, unless the angle is quadrantal, in which case we'll say the angle is quadrantal. So let's do that. Okay, so the directions are to determine the quadrant for each of the angles, for each angle in standard position. So the first angle, pi over 10. If I were to draw that angle pi over 10 in standard position, would it be in quadrant 1, quadrant 2, quadrant 3, quadrant 4, or would it be a quadrantal angle? Well, let's think about pi over 10. Pi over 10. So here's a copy of the axes. Here's pi. Here's 0. Here's pi over 2. I can write pi over 2 as a fraction with 10 in the denominator if I multiply numerator and denominator by 5. So since 5 pi over 10 is pi over 2, then 1 pi over 10 has to be somewhere where? In quadrant 1. If 5 pi over 10 is represents 90 degrees, then 1/10, or 1 pi over 10, then would have to be 1/5 of 5 pi over 10. So that's got to be in quadrant 1. So the answer is, it's a quadrant 1 angle. So B. How about 7 pi over 10? 7 pi over 10. I have a feeling you have the answer right away. If this is pi over 2, and this is pi, and pi over 2 is 5 pi over 10, and pi is 10 pi over 10, then 7 pi over 10 has to be somewhere between 5 pi over 10 and 10 pi over 10. So 7 pi over 10 needs to be a quadrant 2 angle. So let's get a little trickier. C. How about negative, let's see, negative 14, I'm making this up. I don't want to do negative 14. I should have made it up a little. Should have done this off camera. Let's say I want it to reduce. How about negative 11 pi over 10. Negative 11 pi over 10. A little tricky because we have to kind of think about negative angles. So negative 11 pi over 10. Well, here's 0. Well, if positive pi over 2 is 90 degrees, then negative 9 pi over 2 would be negative 90 degrees. But negative pi over 2 is the same thing as negative 5 pi over 10. And then negative pi, which ends up at this in the same terminal position as positive pi, that's like having negative 10 pi over 10. So negative 11 pi over 10 would push just a little bit further into quadrant 2 again. So negative 11 pi over 10 would be another quadrant 2 angle. Okay? I'm going to get trickier still. D. Where is the angle 3? Oops, excuse me. I just dropped my surface. 3. Most often in live lectures, I hear an overwhelming wrong answer by a lot of people. Most people at first are going to say that this angle, oh, 3, it's a real small angle. It's got to be in quadrant 1. 360 is all the way around. And that statement I just made is not true. 360 is not all the way around. 360 is not one revolution. 360 degrees is one revolution. 3 as an angle has no degree symbol on it. Be very careful with this. 3 is an angle measured in radians simply because it has no degree symbol. 3 radians. 3 radians. 3 is in radians. Why? Because there's no degree symbol. Well, it's still a little rough. Here's pi over 2. Here's 0. Here's pi. All of the angles, the two angles, pi over 2 and pi, are angles measured in radians as multiple of pi. Now, they're not measured in radians because they have pi symbol on there. They're measured in radians because they don't have a degree symbol. But my angle 3 is not a multiple of pi. So remember, pi is approximately 3.14. Pi over 2 then is approximately half of 3.14 is 1.57. So 3 has to be somewhere between 1.57 and 3.14. So 3 needs to be a quadrant 2 angle. A quadrant 2 angle. Okay. You might need to think about that off camera a little bit. Okay. E. 3 degrees. So if you're thinking quadrant 1, you're correct. It's a no-brainer. 0 degrees. 90 degrees. 3 is so tiny I can't even draw it. 3 in standard position, 3, and this is, even as the way I've drawn it, I think it's too big. 3 degrees, of course, is between 0 and 90 degrees, is in quadrant 1. Quadrant 1. Okay, we're almost done. F. Pi degrees. The most common wrong answer is that it has to be, oh, it's quadrantal. Quadrantal. Pi is 180 degrees. Well, pi is 180 degrees, but this isn't pi. This is pi degrees. This is an angle measured in degrees. Pi degrees is about 3.14 degrees. Obviously, this is a quadrant 1 angle. Okay. Promise we're almost done. G. Suppose we want to look at the angle 5 pi over 6. Well, there are a couple ways of doing that. We already looked at 5 pi over 6. 5 pi over 6 we looked at, and I'm going to draw it a little more sloppy than I did with my, a lot more sloppy. I guess I could get a circle. I'll try to make it as neat as I can. We've looked at 5 pi over 6 already. Here's 0. Here's pi. 1/6 of pi. 2/6 of pi reduces to pi over 3. 3/6 of pi. 3 pi over 6 reduces to pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6 is before 6 pi over 6. 5 pi over 6 is a quadrant 2 angle. Now suppose I wanted to get that by looking at 5 pi over 6 as a angle measured in degrees. So a second alternative to this would be to convert 5 pi over 6 to degrees. Okay, and there's a very easy way to do that. 5 pi over 6 is in radians. So I could write RAD, although I don't have to because it's unitless. And I could multiply by a conversion factor. I want to end up with degrees, so in the numerator I'm going to multiply by 180 degrees, corresponding to every pi radians. The radians will cancel, the degrees will remain, and in fact, pi cancels. 6 divides into 180 30 times, and 30 times 5, when you do this multiplication, this is 150 degrees, which you may recognize as a quadrant 2 angle, because 150 degrees lies between 90 degrees and 180. Okay, so it's possible to figure out that 5 pi over 6 is a quadrant 2 angle by converting from radians up to degrees. Just as a side note to end this lecture segment, suppose I wanted to convert from degrees to radians. Suppose I have an angle of 12 degrees and I want to convert that to radians. I would do a similar thing that I did in the previous example. I would multiply by a conversion factor that would cancel out degrees and leave radians, so I would multiply by pi radians over 180 degrees. Remember, pi radians corresponds to 180 degrees. The degrees would cancel, and I would end up with 12 pi over 180, or pi, I think this reduces to pi over, 12 goes into 180, 15. So pi over 15 radians. Okay, so you've taken in a whole lot of stuff. This ends our first video segment on angles measured in measuring angles, and an brief introduction to trigonometry. Go ahead and get a good start on homework, also listed on Canvas in the files area. And I'm looking forward to talking again with you all soon.